Hello and welcome to the EC'23 tutorial on information design, one of the most burning research topics of recent years. I'm Konstantin from the Technion in Israel, and I'm going to talk about the algorithmic fundamentals of information design, while my co-organizer Haifeng will talk about new frontiers after the break. First, we'll discuss persuasion in general a bit, and then we'll define the formal mathematical setting of Bayesian persuasion. Then we'll discuss two complementary ways to tackle Bayesian persuasion problem, and we'll talk about algorithmic aspects of Bayesian persuasion. And finally, we'll briefly discuss some extensions. So first of all, what is persuasion? Let's think of a certain advisor who tries to persuade a company to hire her student by writing a recommendation letter. In the letter, the advisor should strategically reveal information in order to maximize the probability of hiring. And this is what we call information design. In a few minutes, we'll define a formal mathematical setting which captures these applications and many, many more. According to a study of 1995 by McCloskey and Klammer, persuasion is responsible for about 1/4 of the US GDP. And a more recent study from 2013 by Antioch updates this figure to 30% from US GDP. And persuasion has been shown in the past to have many real-life applications, which include but not limited to ad auctions, bilateral trade, persuading voters, fighting fair evasion in public transport, and even maintaining physical security. And also, just in this EC conference, we have quite a few papers on persuasion, and this is not an exhaustive list. So once we understood that persuasion is important, let's formalize the setting. So let's think of two strategic agents, sender, for example, an advisor, and the receiver, for example, a company. We assume that there is some information hidden from the receiver, but known to the sender. Let's call it the state of nature or just the state. And it may represent, for example, the quality level of a student. Let's fix a state omega of states. For simplicity, let's assume that it's finite, so the states are numbered from 1 to k, but in general, it needs not to be finite. We assume that there is some prior distribution p on the values of omega, which is also just called the prior, and it is known both to the sender and to the receiver. And there is a certain true state denoted by omega known only to the sender. The setting of Bayesian persuasion is based on the assumption that the sender has commitment power, which means that the sender can commit to a randomized information revelation policy about the state, which we call signaling scheme. This commitment power assumption was introduced by Kamenetz and Gentzkow in their celebrated paper from 2011 called Bayesian persuasion. And among justifications to this commitment power, we can list reputational or legal aspects, or in some applications such as online ad auctions, it can just come from implementing the auction via open source code, which is available to everybody. I should also mention that strategic information revelation is possible to analyze also in a setting without the commitment power, and this setting is called cheap talk. But we'll not talk about cheap talk today. So let's briefly describe what a signaling scheme is. So it consists of distributions over signals conditional on all possible values of the state. And we essentially think of it as a mapping from the states to the signals, So there is a bipartite graph. One side is states and the other side is signals. And on the edges vary the probability that some signal is sent in some states. So for example, here in state 3, probability 0.5 we send signal number 2, and for probability 0.5 we send signal number 4. And we denote the true signal realization by sigma. Note that after the receiver gets the true signal realization sigma, she can deduce a new updated belief about the state of nature. And she can compute the new distribution over the values of the state using Bayes' law. So the computation is fairly simple, and we call the new distribution of the values of the state from the point of view of the receiver after observing the signal, the posterior distribution, or just the signal. So according to Bayes' law, the posterior probability of the state being I, conditional on the signal realization being some sigma 0, is the probability to send the signal sigma 0 conditional on the state being I, multiplied by the prior probability of the state being I, divided by the unconditional probability of the signal realization to be sigma 0. And we assume that the receiver has some actions at A, and after observing the signal realization and computing the posterior distribution, she has to choose some action. And which action would she choose? Well, as I've already said, both agents are strategic, and the utilities of each agent depend both on the receiver's action and on the true state. So the receiver, being strategic, just chooses the action that maximizes her expected utility where the state is distributed according to the posterior belief corresponding to the specific signal realization. And know that the designer in this setting is the sender, and therefore, as is natural, the research focuses on the sender's point of view, which means that we help the sender to choose the best possible signaling scheme overall, in terms of maximizing expected sender's utility over the signaling scheme. Let's describe the persuasion process in details. So first of all, the sender must commit to a signaling scheme sigma, which is a randomized mapping from the states to signal realizations. After committing to the signaling scheme, she observes the value of the true state of nature omega. Then, according to the signaling scheme and the true state, a signal realization sigma is drawn. Upon receiving sigma, the receiver computes the posterior distribution, and she chooses an action A that maximizes her expected utility over the posterior. And in case there are several actions that are equally good for the receiver, the convention is that the receiver chooses the action which is better from the sender's point of view. So this assumption is totally unimportant in practice, but in theory it's really helpful because it ensures that there always exists a signaling scheme which is optimal. Without this tiebreak in favor of the sender, it's not necessary that there exists an optimal signaling scheme. And the existence of the optimal signaling scheme facilitates the presentation. And finally, both agents get utilities according to the actual action chosen by the receiver and the true state of nature. So I'll just check on the chat if there are any questions. I see that there are no questions. So let's continue. And let's demonstrate the persuasion process via an example. So let's only consider a case with just two possible states of nature and a uniform primary distribution over the states. And let's assume that the receiver just has two possible actions, yes or no. let's assume that the sender just wants the receiver to take action yes, which means that sender has utility of 1 for taking the action yes and utility of 0 for taking the action no. And as for the receiver, we assume that if she takes the action no, then her utility would always be 0. But in the state 1, she prefers taking action yes, and formally her utility for taking action yes in state 1 is 1. And in the state 2, she doesn't want to take action yes, and formally her utility for taking action yes in state 2 is -2. So let's demonstrate the full process. So first of all, the sender must commit to a signaling scheme. So suppose that she chooses the following signaling scheme. This is just one example. So suppose that she commits then that when the state is 1, she would send a signal denoted by sigma 1 with probability 1. And when the state is 2, she would flip a fair coin. And according to the realization, she would choose between signal sigma 1 and another signal sigma 2. After committing to the signaling scheme, she realizes the true state, which is drawn from a prior distribution, and suppose that the state 2 was drawn. So now the sender knows the state, but the receiver doesn't know the state. She still only knows the prior for now. Now, according to the state being 2 in the signaling scheme, a signal realization is drawn, so it is half probability half to be sigma 1, probability half to be sigma 2. And let's assume that sigma 1 is chosen. Now, the receiver should compute the posterior according to the signal realization being sigma 1. So I won't present the full computation using Bayes' law, but intuitively, why is the posterior to sword? So originally, the probability for each state was 1/2, 1/2. But because the probability to send the signal sigma 1 in state 1 is twice the probability to send this signal in state 2, to balance it, upon getting the signal sigma 1, the posterior probability that the state is 1 must be twice the posterior probability that the state is 2. And therefore, the posterior is 2 sorts for the state 1 and 1 sort for the state 2. And now let's understand which action is better for the receiver. So the easy part is that because for the no action, the utility of the receiver is always 0, then of course her expected utility for action no is also 0. But let's understand what happens for action yes. So according to the posterior, there is a probability of 2 sorts for the state being 1, and in this case, receiver's utility for action yes is 1. And this is the explanation for the term 1 times 2 sorts. And now, what happens when the state is 2? So receiver's utility is -2, and the probability for it is 1 sort. And therefore, the expected utility of the posterior for taking the action y for the receiver is also 0. So the receiver is indifferent between the two actions, but since we assume that the tiebreak is in favor of the sender, and the sender prefers action yes, we assume that the receiver would choose to take action yes. And the sender would get utility according to action yes and state 2, which is 1. And also there is the receiver's utility, but as I've already said, we focus on the sender's point of view because the sender is the designer in this setting. So any questions by now? Because this is the finish of the demonstration of the basic setting. And now we'll start describing the results. Okay, no questions. So let's present the first approach for tackling Bayesian persuasion, which is called straightforward policies. This approach allows to transform the sender's optimization problem to a linear program which is solvable in time polynomial in the number of states and the number of actions, which is not always good enough because in many applications first of all, at least one of them may be even infinite, but even if it's finite, so I'll just briefly mention one application, so online auctions. In an online auction, the receiver is an advertising platform such as Google, and so this is the sender, and the receiver is a potential advertiser. The state of nature is a vector of possible attributes of the user of the platform. And if there are just n attributes for the user, and each attribute has only two possible values, then already we have to do the n states. And therefore, a polynomial running time in the number of states is probably not good enough in this common example. So in theory, it is good, but not always in practice. But anyway, let's go over this approach. So signal scheme is called straightforward if for each action attached is a signal, a possible signal realization, and we treat the different signal realizations as sender's recommendations to take a specific action. And the requirement is incentive compatibility, which means that the receiver will always better off an expectation by following sender's recommendations. So sender just recommends the receiver actions in a way which is indeed incentive compatible for the receiver. So there is a proposition saying that there always exists a signal scheme which is optimal, and it is also straightforward. And it is obviously an analog of the evaluation principle and mechanism design. So the idea is if you have two signals that result in the receiver taking the same action, then essentially you can replace them with one new signal. But there is a gap in this argument, because essentially what you're doing is replacing the two posteriors which yield the same action with their weighted average in the signal scheme. But it's not immediately clear that the new posterior, which is their weighted average, will result in the same action being the best for the receiver. But it's not hard to show that the set of posteriors yielding a specific best action from the receiver's point of view is convex, and therefore this argument is valid. So you do need some convexity argument, but it's quite easy, so I skip it due to the lack of time. But I will demonstrate how you can use the knowledge that there always exists an optimal signal scheme which is straightforward in practice. So let's put numbers in the leading example of advisor and company. So suppose that there is a probability of 1/3 that the student is good, and the probability of 2/3 the student is bad. And I remind you that the possible actions are to hire or not to hire the student. So since the advisor just wants the student to be hired, let's assume that advisor's utility is 1 upon hiring regardless of the state, and 0 upon not hiring regardless of the state. And the company, on the other hand, wants to hire a good student and not to hire a bad student. So let's assume that the company's utility is 0 upon not hiring, but it is 1 upon hiring a good student and -1 upon hiring a bad student. Now let's formulate a linear program for the advisor's optimization problem. So first of all, the variables here respond to the freedom degrees in the optimization problem of the advisor. So X good hire is the probability that the advisor recommends hiring conditional on the student being good. And X bad hire is the probability that the advisor recommends hiring conditional on the student being bad. And since 1/3 and 2/3 are the probabilities of the student respectively being good and bad, the objective function here is just the sender's expected utility upon a straightforward policy. But we also must ensure that the recommendations are incentive compatible for the company. So first of all, there is an obvious requirement since we're talking about probability distributions that the probabilities of recommendation must be between 0 and 1. And also, I ignore the probabilities of recommending not hiring because these are just 1 minus the probabilities of recommending hiring in the corresponding states. So let's try to understand the two constraints. So the first constraint exactly says that in expectation, the receiver weakly better off when the sender recommends hiring to indeed hire rather than deviate to not hiring. Yes, because we subtract from receiver's expected utility upon hiring the 0 utility, which is just the receiver's utility upon not hiring. And in the second constraint, we do the same for ensuring that when the receiver is recommended not to hire, then she indeed would better off by not hiring rather than deviating to hiring. And essentially, it's easy to see that the second constraint is not really essential. It can be dropped, but let's not get into this because we have a short time format. But one point we can see from this formulation is that the constraints are weak inequalities and not strict inequalities. And here, the assumption that the tieback rule is in favor of the sender comes into play, because it's enough require that the receiver weakly betters off upon following the recommendation to ensure that she will indeed follow the recommendations. So easy calculations can solve this linear program, and it turns out that when the student is good, in an optimal policy, the advisor should always recommend hiring, but if the student is bad, she would still benefit from recommending hiring the student with probability 1/2. And intuitively, it's true because upon getting the recommendation of hiring, it makes the company indifferent between hiring and not hiring, and we assume that the ties are broken in favor of hiring. So any questions by now? Because we finished the first approach, and now if you don't have any questions, we'll go to the second approach, which is called quantification. So you can still think if you have any questions by now. So let's revisit the Zabarnyi scheme compared to what we've thought about it by now. So as is standard for any set S, we denote by delta of S the set of all distributions over the elements of S. Note that a Zabarnyi scheme, being a randomized mapping from the states to distributions over signals, in particular, it also induces a single unconditional over the state distribution over signal realizations, and therefore also over posteriors. And from this point of view, we can consider the Zabarnyi scheme to be just a single distribution over posteriors, yes, distribution over distributions. So we slightly abuse the notations, and we consider the Zabarnyi scheme to be a distribution over posteriors unconditional over the states. And the question is it true that any distribution over posteriors specifies Zabarnyi scheme? And the obvious answer is definitely not. Because, for example, if there is a positive probability that the student is bad, then of course it's not possible to implement a Zabarnyi scheme that will always induce a posterior that makes the company believe with probability 1 the student is good, because there is a positive probability the student is bad. So the necessary and sufficient condition for distribution over posteriors to correspond to a Zabarnyi scheme is called base plausibility, and it requires that in expectation over the Zabarnyi scheme, when we refer to the Zabarnyi scheme being an unconditional distribution over posteriors, the requirement is that coordinate-wise, the expectation of the posterior must be the prior. So the sender can play with the belief of the receiver in every iteration separately, but not an expectation. And why is it true intuitively? So the name splitting lemma of this condition suggests about what happens here. So suppose for simplicity we have only three states and some prior distribution P inside the simplex of all the distributions over these three states. So what can be done by the sender is just splitting the probability mass in the prior to several posteriors. The requirement is that the weighted average of these posteriors, which is just the covariance combinations of them, it must be equal to the prior. So this is essentially the freedom of the sender. What can be done in the signaling schemes. And once we have this characterization of the inducible signaling schemes in terms of distributions over posteriors, once we also agreed even before that we only focus on the sender's point of view, let's get rid of the receiver's utility and even of the receiver's action. And as a side effect, let's also ignore the dependency of the sender's utility on the state, because it's a bit inconvenient to tackle technically. So we'll define a new function called indirect sender's utility and denoted by U, which is just sender's utility where the argument is the posterior distribution. So indirect sender's utility is a function of the posterior distribution. And it can be calculated from the sender's utility as a function of the action and the state, just by taking the expectation when the state is distributed over the posterior, and the action is the single action which is induced by this posterior. And from now on, let's agree that we're trying to help sender to maximize the expected indirect sender's utility over all signaling schemes, where the posterior distributed according to the signaling scheme, which is an unconditional distribution over posteriors. We just induce one benign assumption on the indirect sender's utility, which is upper semi-continuity. And as an illustration, you can see this graph of function in the right side of the slide. Upper semi-continuity means that the lim sup of this function at any point must be at most the value at this point. And in particular, for example, each continuous function is upper semi-continuous. Intuitively, in terms of persuasion, we think of upper semi-continuity as the requirement that the ties are always broken in the sender's favor, because the discontinuity points essentially correspond to the receiver switching from one action to another. And if the receiver has freedom of choice, has indifference between several actions, we want her to choose the action which is best for the sender. And this is exactly upper semi-continuity. And this condition ensures existence of an optimal signaling scheme. But this condition is truly general. So the goal is to maximize the expected indirect sender's utility. The sender's utility is a function of the posterior over all possible signaling schemes that are bias plausible, which means, I remind you, that the expectation of the posterior must equal the prior. And this is the only requirement. And if you really want to, you can go back to the conditional distributions over posteriors, and you can define the signaling scheme according to our original definition if you really want to, using Bayes' law, up to renaming the signals. But usually it is omitted in the storage because it's truly straightforward using Bayes' law. And now a very important notion is the concavification of a function. So given some function, its concavification is the pointwise minimum of all the concave function which are never below the given function. So it is a concave function which is pointwise minimal among all functions that upper bound the given function. So for example, for a concave function, the concavification is this concave function itself, while for the black function here, the concavification is this thread function. And now, given this notion, we're able to present the main theorem of the second approach to Bayesian persuasion. And it goes as follows. When we know the indirect standard utility U, and we want to evaluate the optimal expected standard utility, then we just have to evaluate the concavification V of the indirect standard utility when we plug in the posterior which equals to the prior. Again, the optimal expected standard utility is just the evaluation of the posterior at the prior distribution. And moreover, there is a one-to-one correspondence between all the optimal signaling schemes and all the ways to represent the point on the graph of the concavification of the indirect standard utility corresponding to the prior as convex combinations of some points on the graph of U, where the elements of the graph of U participating in the convex combination would be exactly the support elements of the optimal signaling schemes, and the weights in this convex combination would be exactly the probabilities to induce these support elements. So in a second, I'll demonstrate an example, but the idea behind the proof is as follows. So let's fix some upper semi-continuous function U offers basically a continuous function, and there is also some prior P. Now the concavification of this function U is this red function. So let's consider the point on the graph of the concavification V corresponding to the prior. So we know from splitting lemma that the freedom that the sender has is to split the prior to some posteriors, provided that the expectation of the posterior remains the prior. And if we also want the expected utility of the sender come into play, then it is exactly to say, then this point, which is the prior, comma, the expected standard's utility of the theorem scheme must be some convex combination of points of the graph of U. And each point on the concavification has indeed such a representation. And why cannot we go above the concavification? Well, it's because from the splitting lemma, we cannot leave at the convex hull of the points on the graph of U. And the concavification is exactly the supremum of the points in the convex hull of the function U. So this is the proof idea. And now let's demonstrate the application of the main theorem to the example of recombination letters, our written example. So recall that there is the probability of one sort for the state being good and two sorts for state being bad. And there are two actions higher, not higher. The advisor just wants the receiver to hire, while the company wants to hire if and only if the state is good. And the utility of the company upon not hiring is always 0. So let's compute the indirect standard's utility. And because there are just two states, we can actually consider the indirect standard's utility to be a function not of the posterior, but only of the first coordinate of the posterior, because they sum up to 1. It's a distribution. So let's compute U as a function of the posterior probability of the state to be good. So the company would hire the student if and only if the probability that the student is good is at least as high as the probability that the student is bad. And therefore, if the posterior probability the student is good is at least 1/2, then the indirect standard's utility would be 1 because hiring occurs, otherwise it would be 0. And therefore, the indirect sensitivity is the black function u here. So below 1/2 probability for the scenario to be good, it is 0, and above 1/2 it is 1. The quantification of this black function is the red function v. So the prior in this example is 1/3, and therefore the optimal expected sensitivity is the evaluation of the red function at 1/3, which turns out in this example to be 2/3. And the optimal signaling scheme, so there is just one in this case, and it is the support elements are the only points on the graph of the black function u, the closest combination of which can be the point on the graph of v corresponding to the prior, which are 0 and 1/2. And if we complement them to a distribution, because the posterior is distribution, it would be 0, 1, and 1/2, 1/2. And the weights are just the probabilities to induce the support elements. So any questions about this example and the main theorem in general? So if not, then just let's go over easy corollaries, easy but important, and then let's see algorithmic aspects and extensions. So if the indirect sensitivity is concave, then its quantification coincides with itself, and therefore the normal evaluation policy is optimal, which means that the posterior is always just the prior, with probability 1. On the other hand, if indirect sensitivity is convex, then the full evaluation is optimal, which means that it's always good for the sender to reveal the true state. While if the indirect sensitivity is linear, then the signaling scheme is not important at all. And now for the algorithmic aspect. So there is an excellent story by Shadin Dugmi from 2017, but there has been some progress since then. So a paper by Dugmi and Shu from 2016 studies a setting with independent senders and receivers payoffs, and they call each possible value for the senders and receivers payoff for some action a type. And they studied the computational tractability of persuasion in terms of the number of tighted states. And it turns out that in general, for independent payoffs, it's intractable, but when the payoffs are IID, it is tractable. Also, consider general actions with payoff distributions given by sampling black boxes. They derive an additive bicriteria of Pitas, which runs in time polynomial in 1 over epsilon the number of actions, which is epsilon far from being optimal and epsilon far from being persuasive, and they prove that the bicriteria loss is inevitable. And there are many extensions of the basic setting. So arguably the most common ones are for multiple receivers. So either you study private multi-receiver persuasion in which the sender is allowed to communicate privately with different receivers, or public persuasion in which the sender is forced to reveal exactly the same information for all of them. And when you're talking about algorithmic aspects, you should distinguish between the setting without and with externalities. So the simpler setting is no externalities, which means that there are multiple receivers, but the utility of each receiver only depends on the true state and her own actions. But it's independent of the actions of the other receivers. If we drop this assumption, we allow the utility of a receiver to depend also on the actions of other receivers, then we are in a much harder problem. So let's start with the private persuasion non-externality case. So a paper by Dugmi and Shu shows that persuasion in this case is tractable if and only if it's possible to do unconstrained optimization for sender's utility plus any linear function. And in case of binary action receivers, Sender's utility is essentially a set function. It's a function of the set of receivers taking a certain action. And when this set function is supermodular and submodular, previous papers by Barman and Babichenko and Babichenko show that that the persuasion is tractable, but in the general case of submodular Sender's utility, it is intractable, and it is known that 1 minus 1 over E approximation ratio is possible, and it's tight. Now, for public persuasion without externalities, it's intractable in general, even for additive Sender's utility, but it's tractable for a constant number of states. For public persuasion with externalities, it's NP hard even for two receivers with a zero-sum game, but under some smoothness assumptions, there is an additive PTAS for the optimal expected Sender's utility. And the private persuasion with externalities remains much unexplored, though there are some papers studying special cases, such as congestion games and applications to stress testing. There are more extensions, such as applications to multi-channel persuasion. Multi-channel persuasion means that a sender can communicate with overlapping subsets of receivers. For example, it is reasonable to assume that this is a case when the sender is, say, a politician that tries to persuade voters via different channels in social media. So there are settings in which multi-channel persuasion is harder than both private and public persuasion, but still under quite a general special case, it's possible to derive an additive FP-TAS. So a constant number of states is essentially required because even public persuasion is hard for a non-constant number of states with additive utilities. But also in this special case, there is one more requirement that the receivers are organized in a forest structure in terms of the information they get. Also, we might want to restrict inter-point pattern expectation the support of the Stevenin schemes, which may originate for example, noisy communication or rational annotation of the receivers, or in auctions, this constraint may come from the desire to ensure fairness, either in each persuasion instance separately or an expectation. And now let's conclude this part by mentioning some robustness notions. So there are plenty of study of robustness. We'll just mention two of them. So there is robustness to receiver's utility, which you can either study in an online learning setting, trying to minimize the regret over many iterations. And it turns out that getting sublinear regret is computationally hard in general, but it's tractable when Sender's utility is submodular. And also you can try to minimize the regret in a single shot game over just one iteration. And in this setting of a single shot game, it turns out that knowing receivers' online preferences makes the difference between ensuring virtually no guarantees and ensuring a regret which is relatively good. And online preferences might be reasonable in practice, because, for example, when you advertise a phone, you may assume that the buyer would prefer buying a lighter phone rather than a heavier one, but maybe not up to which extent. And finally, robustness to prior means that maybe the receiver has some exogenous source of information about the prior, and there is some work on this. For example, there is no characterization for a binary action receiver for the case of state-independent Sender's utilities. Thank you very much and enjoy the break.